Hello, this is the updated part 3 of the Math 1813 Prep for Calc final review from the MLSC. We are reposting this in 2023 as there's been an update to the final review. So these will not necessarily, there will be different voices from part 1 and part 2 since they're from last year. But without further ado, we'll do question 17. A Ferris wheel stands on top of a building so that the riders aboard the Ferris wheel at its lowest position, a height of 100 feet above ground level. The Ferris wheel takes 6 minutes to make a full revolution. So I'm going to go ahead and draw this. That's how it. Okay. So we start at 100 feet above the ground. And then we start at the bottom. They go up, and they come back down, and they go up again. So the full period is 6 minutes. They go all the way around in 6 minutes. So up and then down and then up. So this is 6 minutes. So we're asked, so we're 6 minutes to make a full revolution. Riders are at a height of 145 feet above the ground level at 1.5 minutes. So 1.5 minutes is right here. So we can think about our period split into 4 pieces. So in the first quarter, we're going to be halfway up. And so this tells us that our midline is at 145 feet. And that's because 1.5 is a quarter of our period. So we're going to assume a rider's height above ground level h can be modeled by a sine or cosine function of time t minutes after the rider boarded the Ferris wheel. Okay, so we're asked, is this a sine or a cosine function? Assuming there's no shifts, obviously you can rewrite sine in terms of cosine in terms of sine if you shift them by pi over 2. We're going to use cosine because at 0, it's 100 feet. It's at a minimum. So we're going to say cosine. And then we say, what is the amplitude and what is the value of A? The amplitude, because the midline is 145, the amplitude would have to be 45 because the lowest point is 100. So for the midline to the lowest point is 45. Or the highest point, right? And so the value of A is negative 45 because it's reflected. It's a reflected cosine. Because regular cosine achieves its maximum on the y-axis, and this cosine achieves its minimum on the y-axis. What is the period and what is the value of B? The period is 6 minutes. B is 2 pi over 6. So B is pi over 3. What is the midline and what is the value of K? The midline is y equals 145. And K is equal to 145. So our function is h, and I'll write this right over here. H is negative 45 cosine of pi over 3 t plus 145. Great, okay, 18. We want to sketch the graph of a transformed tangent function with vertical asymptotes at every odd integer and passing through the point 0, 1 and 0.5, negative 3. We want to use our graph to find a possible formula of the form f of t is a tangent of bt plus k. So I'm going to do my best to freehand this tangent graph. So we want axes. So it's going to have vertical asymptotes at every odd integer. So I'm going to go 1, 2, 3, 4. To get the scaling down. Now put in some of these asymptotes. Okay, this is not scaled well, so I'm actually going to restart. I'm going to rescale it a little bit. So we're going to say, so this is 0.5, 1. So each dash is 0.5. And then, so this is 1.5, 2, 3 is over here, 4, 5. Okay, cool. So our asymptotes are on the odds. Like that. And then we have, it passes to the points 0, 1. So I'll call that 1. And then it passes to the point 0.5, negative 3. It's over here. So it looks something like, so this obviously, I'm actually gonna go back on. That's not quite what I wanted. So we want, so it's gonna blow up this way, right? It's gonna come back and it's gonna go down and blow up that way. Obviously not the not the cleanest picture of tangent. I might try and fix that one more time. Okay. This is 0.5, negative 3. This is 0, negative 1. So it comes down to very smooth. Okay, that's a little bit better. I'll leave that up. So it's something like that for all of these. And all of these are gonna, obviously it's periodic, so it's gonna repeat. Okay. And we're supposed to, now that we have this graph, we want to find a possible formula for f of t. So y is, well, first of all, because tangent is going to positive infinity on the left asymptote and negative infinity on the right asymptote, we know that it's negative. There's some scaling factor. And then tangent. And then we know there's some new period. And we know there's a midline. So the midline should be at 0, 1. Well, because when we plug in 0, tangent of 0 is sine of 0 over, it is 0. Tangent of 0 is 0. So our midline should have to be 1. Because we have asymptotes at every odd integer, we should be able to deduce that, so tangent is undefined, so tangent is sine over cosine, so it's undefined when cosine is, when cosine is 0. So we want cosine to be 0 for odd multiples of our period. So cosine is 0 at pi over 2, it's 0 at 3 pi over 2, it's 0 at 5 pi over 2. And so we know that our tangent, the period would be pi over 2x. The last part is, we're going to use this point over here, this 0.5, negative 3, to tell us the scaling factor. So tangent of, so negative a tangent of pi over 2, 0.5 plus 1 equals negative 3. And from here, tangent of pi over 2 times 0.5, that's negative a tangent of pi over 4 plus 1, which is negative a times 1 plus 1, negative 4, or negative 3. So a, so we get negative a equals, right, negative 4, and a equals 4. So y equals, I'm going to move this, y is equal to negative 4 tangent pi over 2 x plus 1. Cool. Okay, Next, we want to find exact values of each of the following, given that tan of theta is 5/2, and theta is between pi and 3 pi over 2. So theta is in the third quadrant. Because theta is in the third quadrant, we know that, well, because pi to 3 pi over 2 is in the third quadrant, we know that cosine has to be negative, sine has to be negative, and then secant would also have to be negative. So all three of these should be negative. The other thing we want to do is draw a triangle. So here's our right triangle. This is theta. Tan theta is opposite over adjacent, so 5, 2. And then by Pythagorean theorem, this has to be the square root of 5 squared plus 2 squared, which would be 29. So now cosine of theta is adjacent over hypotenuse, so it's negative 2 over root 29. Sine theta is opposite over hypotenuse, so it's negative 5 square root of 29. And secant theta is 1 over cosine theta, so it's negative root 29 over 2. And so that's 19. It should be fairly straightforward. Just make sure you know where your theta is, because that's going to tell you the sign of cosine and sine. From there, you're going to build a triangle, and then you know the side relationships of cosine and sine. So for 20, we want to find approximate solutions to the following equation on the interval from 0 to 2 pi. We'll round to 2 decimals. So this would be, we start by just solving this. So I'm going to move the 5 sine over and subtract 40. So I end up with 100 sine of t equals negative 43. And so I get sine of t equals negative 0.43. So we're going to make some observations, and then we're going to use our calculator. So sine of t being negative tells us that we're either in the third or fourth quadrant. So once I find my theta, I want to represent that there's a solution in the third quadrant, because I'm in 0 to 2 pi. Because I'm in 0 to 2 pi, there's a solution in the third quadrant, and there's a solution in the second quadrant. So I'm going to go over to my calculator, and I'm going to say t is arc sine, or sine inverse, negative 0.43. And I have a calculator right here, so let me type that in. Okay, so I got arc sine of negative 0.43 is negative 0.044, approximately. And we want approximate solutions, so that's fine. Here's the problem. This is not in our interval from 0 to 2 pi. So what I'm going to do is I'm going to add 2 pi. So this is in the fourth quadrant, because I know that it's negative and it's less than pi over 2. So I'm going to add 2 pi to negative 0.44. So I'm going to do 2, and I get 5.84. 5.84 is one solution, and that's in the fourth quadrant because it's just slightly less than 2 pi. Now I want to find the same equation in the third quadrant. So I'm going to subtract...
All right, for number 21, we're looking at this graph of two different functions. And part A asks, which one is larger, lowercase a or capital A? So we're looking at this one and this one. And so the lowercase a is going to be larger since it's that initial value of the f function. And we see if we look right here that it's positive, it's above the x-axis. And that the capital A from the cosine function, we know that's negative since the cosine graph that we see is reflected. It's multiplied by a negative number. So we know that lowercase a is positive and the capital A is negative. So the lowercase a is larger. For part B, we want to look at which of the constants are definitely negative. And so we have the options of A, lowercase a, K, and capital A, B, or C. And so here, K and capital A are definitely negative. And so we know that for K because it's an exponential decay. We see that as X increases, the value of the function decreases, so that K value in the exponent has to be negative. So K, and then like I said in the last problem, the cosine graph is reflected over the x-axis. So that means that capital A has to be negative as well. And then for part C, which of them are definitely positive? And so lowercase a and capital C are definitely positive. Lowercase a is like what I talked about in part A, because it's the initial value of the exponential decay function and it starts above the x-axis, so we know that it has to be positive. And then we know that C has to be positive because it's the midline of the cosine graph, and it's approximately just somewhere around here, right? And wherever I draw that line, I know that's going to be positive, even if it's not exactly right there. All right, so for number 22, we're given two functions, and we're going to talk about some composite functions and adding them together. So, yeah. For part A, we're doing f of g of x, okay? So this is just going to be wherever there's an x in f of x, we're going to replace it with g. And so this will make it equal to 1 over x plus 3. We have like a 1 on the top and a fraction on the bottom. And when we're dividing, it's the same thing as multiplying by the reciprocal of the fraction. So that's what I'm going to do. I'm going to say this is the same thing as 1 times x plus 3 over 1, which turns this into just x plus 3. Okay? And so we see that from where this function comes from, now that we're looking at the domain's going to go from negative infinity all the way to negative 3, and then union negative 3 to positive infinity. And this happens because if we look here at the original way we wrote this, there's an x plus 3 in there, that if that part of it, specifically this fraction, if that part of it in the denominator of that fraction, if x was equal to negative 3, we would be dividing by 0, which we don't want to happen. So that's why we need to have that union, because there's a hole that exists when x equals negative 3. So for part B, we're now going to look at g of f of x. So g of f of x. And so this is going to be wherever there's an x in g of x, we're going to plug in f of x. So this will be 1 over x plus 3. So to simplify this down a little bit, I'm going to multiply this fraction by x over x, which this is the same thing as 1, so it's not actually changing the value. And so we're going to look at this, and it's going to transform it into x over 1 plus 3x. Okay? So this is our function. Let's look at the domain again. Okay? So here, it's going to go from negative infinity to negative 1/3, union, negative 1/3 to 0, and then union 0 to positive infinity. Okay? So let me explain some of why these holes are happening again. Okay? So here we have this fraction where if x is equal to 0, we'll divide by 0. So we have a hole there. Also, if we look here, if x is equal to negative 1/3, we'd have 1 plus 3 times negative 1/3, which becomes 1 plus negative 1, which would again result in us dividing by 0, so we have another hole. So besides those holes, x is good for all real numbers. Okay, now we're going to look at part C, which is f of x plus g of x. Okay, so this is equal to 1 over x plus 1 over x plus 3. And so I need to find a common denominator here. And the common denominator is just going to be x times x plus 3 because there's nothing else we can use. And so I will have x plus 3 times 1 on the left fraction plus x over x times x plus 3. This is the combined fraction. I'm going to keep simplifying here. So this is 2x plus 3 over x times x plus 3. Okay. Now let's look at the domain of this again. It's going to go from negative infinity to negative 3, union, negative 3 to 0, union, 0 to infinity. Okay? And this makes sense because if we look at the denominator of our fraction, if x is 0, we'll divide by 0, and if x is negative 3, we'll divide by 0. So there's holes at 0 and negative 3, so this explains the unions in our domain. Now looking at number 23, it says to find formulas for g of x and h of x, given that g of h of x is equal to 1 over x plus 6 squared, and h of g of x is equal to 1 over x squared plus 6. So this one, you kind of just have to look and see what's going on. So what I see is that when we have g of h of x, is that we have 1 over x plus 6 squared. And I see that x plus 6 could be a function of its own. So I'm going to guess that h of x is x plus 6. And so if I run with that, and I look at h of g of x, then I see that what replaces the x is a 1 over x squared. So I think that's what g of x is. Let me just check this to be sure. If I look at g of h of x, and I replace any of the x's in g of x with h of x, I'll get 1 over x plus 6 squared, which is what I needed. And then h of g of x, if I took wherever the x's are there and replaced it with g of x, I would get 1 over x squared plus 6.
Okay, so number 24 says, this function represents the temperature of a cup of coffee in degrees Fahrenheit after t minutes after it's poured. So we want to find a formula for the inverse function, meaning this is a function of time that you plug in time and you get back the temperature. But we want a function that you plug in the temperature and you get back the time. So I'm going to start writing over here. So I'm just going to write out the function first. So to get a function where you plug in the temperature and you get back the time, well, we just have to solve for the temperature. So let's subtract 75 from both sides. Well, now let's divide by 110. Well, now we can take natural log of both sides to bring down that exponent. And then we can divide by natural log. Divide by a natural log of 0.9. I should be a little more specific. Well, there we go. That's a function for t. Yeah, so that is our function. So here's a function f of h, or f inverse of h. I'm going to write it up here. F inverse of h, because notice now we plug in h, and we get back t. Just what we want. So there we go. There's our inverse function right there. Okay, so part B says evaluate the inverse of 150 and explain its meaning in terms of the cup of coffee. Round to 1 decimal. Okay, well, we can do that. This just means we're going to plug 150 in for this function. So this would be, oh, that is a nasty looking, where's the undo button? There we go. So 150, well, here we'll take our inverse function that we just got from the last part, and we're going to just plug in 150 for h. 75 over 110. Log of 0.9. This is going to be a little work in the calculator. And after consulting my calculator, we get 3.63506. Well, let's round to 1 decimal place, so that'll be 3.6. So what does that mean? Well, remember the inverse function, you plug in h, where h is the temperature in degrees Fahrenheit of the coffee. So what this means is that whenever the coffee is 150 degrees Fahrenheit, and then we get back time from the inverse function, right? So whenever the coffee is 150 degrees Fahrenheit, this happens at 3.6 minutes after it is poured. So there we go.